Welcome everyone. Almost over, I promise. So we're going to shift gears a little bit, talk about reliability, hardware reliability specifically, and specifically looking at modeling and detecting silent data corruptions in the wild. So David and I are going to be presenting, but there's a whole bunch of work being done by a whole bunch of students, so just acknowledging them here. So in this talk, I'll first introduce the problem of hardware aging. So there's multiple reasons why you can have silent data corruptions. We're going to focus on aging in the context of this talk. That's the first thing we're looking at. And why do we want to, so we want to detect aging, and we want to do this at runtime, right? So we want to do this at scale. Hopefully, we can have some runtime detection mechanism for these errors at a large scale. We can deploy it in a data center, and so on, improve cloud reliability. And the approach is going to be a bottom-up approach, and I'll explain what that means in a bit. So aging is important because it's becoming a problem. These days, we're very excited when we get sort of 7 nanometers in a chip, or 5 nanometers, or sometimes 3 nanometers, right? So we can get that too. But you're only excited till you realize that actually 7 nanometers is just 35 silicon atoms put next to one another. It's pretty small, actually. So the problem is, this is very sensitive and easy to degrade, and all of a sudden we could actually lose our excitement. So people have observed this, right? So there's really interesting papers from Meta and Google that first came out and talked about these errors in the wild. And there's actually an SOSP paper from Alibaba coming up in 10 days, right? So there's some really interesting data on how these things manifest at scale. So these are CPU cores that work fine most of the time, but they will occasionally produce a wrong result during certain computations. And according to a recent talk by Google, actually 0.1% of the CPUs in their data centers actually are susceptible to such issues, which is actually a very, very large raw number. So to make things even more scary, Google also unveiled that 88% of their failing CPUs actually initially passed the pre-production testing, which means that they were in good shape when they came out of the factory, but somehow they broke down after being used for a while. So these are some terrifying facts. And so just to summarize the terrifying facts, first, a good CPU may become defective at any time, right? So effects like aging, like thermal effects, like the Alibaba paper has really interesting details on that, and other electrical effects may accumulate over time. The further complicating thing here is that a bad CPU may actually look good most of the time, and that's a problem too, right? So that's, defects may require very specific trigger conditions like frequency, temperature, workload, and that kind of stuff. So that's a problem because that's not the failure model we like. So we like a fail-stop model. So we understand that model, we know how to deal with it, and software assumes we can build software with that model, right? And this is just not the case, and we need to fix this, and fix it in a hopefully systematic way. So how are we going to make a hardware fail-stop like it used to be? Because if hardware is fail-stop, right, we know that, as I said, we can deal with this kind of problem. Now, one idea is to test hardware frequently, right? We can do that with some well-designed test cases. So whenever we find a CPU failing a test case, we crash the application, enter in some sort of error handling mode, and if we test frequently enough, we can identify the failing CPUs as soon as possible, decommission them, etc. Maybe it's under warranty and so on. So even if this is not technically the fail-stop model, it's close enough. Another idea is to run the test within the application itself, if you can find a clever way to actually do that. This way, you don't have to sort of context switch, so to speak, for running these tests. And this would allow us to use the test in a sort of smarter way and maybe do at-scale analyses. So there's some work, of course, in this space. Unfortunately, it doesn't really achieve efficient runtime detection. And the main reason for that is, so test case generation is sort of top-down, I would say, just top-down. So what do I mean by that? So so we have the CPU at the bottom, right? Usually a black box. We consider that as a black box often. Then there's the ISA and the ABI, which sort of is used to describe that black box. And above that, people build libraries and applications and so on. And so there have been multiple approaches to actually testing for these kinds of defects. For instance, Intel has this tool called DC-Diag, an open DC-Diag. These are based on applications and libraries. So you have some experts at Intel that they study hardware components and they come up with this test suites that you can run. You start running them for 45 minutes. They exercise certain code paths in certain ways, and they may or may not find errors. And there's this other tool from Google called SillyFuzz that generates a bunch of test cases using fuzzing. And because the CPU is this sort of closed black box, the way actually SillyFuzz generates these test cases is by relying on a sort of a CPU simulator like QEMU, right? Get some insights from that, and then using those insights, generate test cases, and then drive those test cases. And it actually can generate like 500,000 test cases or so. So that's many test cases, right? It's difficult to sort of like manage their deployment and running. So how can we improve this? Well, actually, if you look at this closely, like CPU is not necessarily a total black box, right? So it's basically someone writes software like Verilog, and then that sort of gets turned into a netlist, which is sort of a bunch of gates and cells. And then those gates and cells are from a standard library typically, which describes the kinds of elements that the chip maker can produce. Now, unsurprisingly, the VLSI community has done a whole bunch of research related to aging, and they have quite a bit of knowledge about aging, and sort of like models at the gate level of how aging works. So specifically for the most important aging effect, NBTI, or negative bias temperature instability, there's quite a bit of understanding of how it actually manifests in standard cell libraries. So here, what you require is a trace of the circuit execution, and the model can give you specific gate delays that will change after aging. Now, key insight here is that we can leverage this knowledge to build test cases in a bottom-up manner and provide software developers with a way to better reason about these effects of aging. So how does our proposed workflow look like here? So we have 3 phases, really. In the first phase, we do potential defect discovery, right? So this is about trying to localize components that are easier to fail, right? So, and we use the previous research from the VLSI community. So we have some collaborators in Technion who have a good understanding of how aging in circuits work, and so we can take that as a sort of first step here to do potential defect discovery. The second phase is called defect lifting, which takes the potentially defective paths that we found in the first phase and then generates a bunch of test cases. And I'm going to get to this. This sounds straightforward, but it is not that straightforward to do, actually. And the third phase is some form of runtime deployment, in which case we want to sort of maybe fuse the logic of these test cases with the application itself and perform the testing at application runtime, and hopefully we can do that at scale. So to understand phase 1, I'm just going to talk about this briefly. So basically, you need to reason about what kind of defects can be induced by aging, right? So aging increases gate delay, which eventually makes the timing constraints that you need to satisfy on certain circuit paths unsatisfiable. So here, this is a circuit. So these are flip-flops or registers, right? And everything here is from sort of a standard. We can assume everything's from a standard cell library. So among these cells, as I said, A and B, they are sort of special cells. They maintain state, right? And they're connected to a clock signal. And there's a certain expectation. Let's say B has a certain expectation that signals from A will propagate to it in a certain amount of time. And what happens is that along the signal propagation path, there will be multiple other cells, multiple other operations potentially, right? And each incur some delay, and that delay can vary over time and actually increase And it may make it so that the constraints that you need to satisfy when the signal travels here are no longer satisfiable after a certain amount of wear, after the circuit is used for a certain time. So it could be that we could actually produce some wrong value here. All right, so here, this phase is really based on static timing analysis. And together with an MBTI aging model from previous work. And to do this, we basically run a bunch of benchmarks with the circuit and collect a bunch of traces, such as the occurrences of zeros and ones, right, in each gate. And then these traces are fed into this MBTI model, and we can calculate how the gate delay of a specific gate will change over time after being used under certain workload conditions. Then we put the updated gate delay into the static timing analysis, and the analysis will give us a bunch of paths that will violate their timing requirement after being used for a while. So that's the first phase. The second phase is what we call defect lifting. So here, the goal is to generate hardware-level test cases using a model checker and basically identify a sequence of inputs for that hardware module that will, this is trailing here, but that will actually trigger that failure. So the goal is really to activate that potentially defective path from from phase one that I showed before. So how does this look like? So the output of this is going to be a waveform. A waveform like this. Output of this stage is going to be a waveform like this. And the goal is to take this waveform and convert it into a bunch of instructions that can trigger the waveform in hardware. And this may require certain heuristics and some understanding of the microarchitecture as well. It is actually really a program and test case synthesis question. So how do you take certain inputs that you identify to trigger errors, and from those synthesize a program and a test case that will drive these components towards those susceptible paths, right? So you could use model checking here, you do use model checking to get from the netlist of the module and the defective path in that phase one. We can get these, we can generate those inputs, and we want to hit the model checker tool to find us a trace that triggers the violation. And you use sort of classical tools from sort of automated reasoning, really, to actually do this. So you create a shadow copy of the circuit, and then you basically encode a constraint that will say, okay, given the same inputs to the circuit, is it possible to produce different outputs? Because that shouldn't happen, right? So it's a sequential circuit. Is it possible to produce a different output given some aging-related effects? And if it is possible to do that, right, it means there's maybe an aging-related issue going on. So it's really asking the tool to generate some counterexamples. And as I said, if you want to go from trace to the instructions, I mean, for basic things, we can reason about it really easily, right? So if it's an ALU, I mean, we can come up with instructions that will assert that maybe 1 plus 2 is equal to 3, or it's not equal to 3, right? So you can use these as test cases. Of course, it's simple to do that for basic functional units. You can envision targeting a floating point unit or the instruction decoder, so that there's other components, right, in hardware. Or you can target things like cryptographic units as well, right, like the AES unit or like hash generation. So the second phase gives us a bunch of instructions, right? This is really a test case and some input to actually trigger these errors, and we want to use them in a smart way in an application. So one idea, right, is to fuse the application and the test case, where we merge the generated test cases in the same binary, and hopefully we can deploy that in production. And we could do this, for instance, using profiling information. So we can specifically profile the application and select frequently invoked locations in the program where a particular functional unit that you want to test is idle, right? Because the CPU issues multiple instructions. And actually, if the functional units, the ports are available for you to do your testing, you can leverage instruction-level parallelism and sort of overlap computation and do your testing while you're still doing your useful information processing for your application logic at the same time. So it's all about identifying those opportunities. There are different ways you can be clever about doing this fusing and actually deploying this kind of massive scale check at runtime. The other thing, for instance, you can do is you can provide the developers a defect checking library, right? So you can pack test cases in a library, and you can allow people to write sort of defensive code where, for instance, before they're supposed to do something important, maybe compute a hash or a key, they can try to see whether that particular unit is susceptible to wear. And if it is not so, then they can actually go ahead and do it. And if there is maybe an issue, right, maybe they can retry, right? Because these things disappear. So you can selectively implement strategies like triple modular redundancy and so on, which normally you wouldn't be able to deploy, right, at scale because it would be just too expensive. But you can do it in a more targeted and clever way. So we've done some work already on a 32-bit FPU implementation using the TSMC 28 nanometer library and identified 1,000 most timing critical paths. Not going to get into the details of setup and hold, but basically identified module level input sequences that are potentially susceptible to aging related issues. So where do we go from here? So there's a bunch of things we can do. As I said, we can look at different functional units like AES, SHA, and these things, right, can have security consequences as well. Like what happens if my instruction decoder behaves in a weird way? So can I actually hijack the control of the program maybe? Or maybe can I mount a certain kind of cryptographic attack? So those are interesting things to look at. And you can explore more than aging, right? So aging is just one effect. There's other effects that could actually feed into this bottom-up model where you can have electromigration or some other effects that are like thermal effects that you can plug it in right from the bottom of this model and then reason about those as well. We can build some simulators to speed up this exploration, and we can also explore aging-based attacks, which is where David will say a few words, I guess. Right? So aging is just one effect. There's other effects that could actually feed into this bottom-up model where you can have electromigration or some other effects that are like thermal effects that you can plug it in right from the bottom of this model and then reason about those as well. We can build some simulators to speed up this exploration, and we can also explore aging-based attacks, which is where David will say a few words, I guess.
And so my question here is, can we jump ahead a little bit and look at some top-down security implications? So you're telling me that we have data centers that have 0.1% of their CPUs that start misbehaving in interesting ways, and that quite often these faults are going to be not fail-stop, and they're going to affect computation in interesting ways. And so let's assume that this process succeeds and we end up with some sort of interesting fault model that's, and for the moment we're going to assume instruction-centric. And what I mean by that is that if I give you a program, and we start looking at individual instructions in that program, given some instruction, and perhaps a window of the most recent couple instructions, I can make some decision about whether to be able to fault in this program. And so we're going to build a simulator or more something like a fuzzer that's going to help us find whether or not software can break in interesting ways, and we can refine our usage of this as this model that we have that is bottom-up improves. At a high level, the tool that we're working here is this kind of like pin-based harness. We're going to then try and just run actual applications. Mostly we've been looking at things like database servers and whatnot. We're trying to pick application targets that are going to run in a data center. We're not talking about situations where your adversary is co-located with the system. And we build a kind of remote client that's a driver and a test harness for this interface. And what we're going to do is we're going to generate what should look like normal input and output traces to this target application. We get our normal response that doesn't have a fault, and then we start executing with different randomized seeds, and we start injecting faults into this target server application based on these fault models. And we generate what looks like potentially faulty responses. We also generate cases where the application crashes. And the insight that we have here is the situation that we mostly end up caring about for this type of model are the cases that do not crash. We want situations where the program continues to execute correct, like under normal circumstances, but that the output results are wrong. If it crashes, that's a situation where the adversary needs a lot more control over the system to potentially be able to exploit it. But if the program continues to execute normally, let's say you're doing a database query, if the database query executes to completion, but queries the wrong rows, this is potentially extremely interesting to me as an adversary. And so we're going to be looking at these. So we have a version of this tool right now. It's relatively early days, but we do have this kind of fun way to be able to plug in fault models that can do things like you can choose what the fault type looks like. You can choose the instruction types. You can choose when and how often it will fault on those instructions and on different inputs. And we can choose seeds to kind of determine when these faults will occur and highlight for ourselves, okay, we believe these instructions in this binary are likely to be able to fault given the model that we have. So that's all for me at the moment. Hopefully we'll have some cool faults on some server applications next time around, and you'll get to see some neat exploits. Thank you.
So one question I had was, what is the for the hardware fault localization part of it? Is there a baseline in the sense that can we, for instance, give Intel to provide you with a set of sort of instruction checking things which you can run, for instance? So
that'd be great. Yeah. I mean, if we could do that, we wouldn't go down the road of coming up with a fault model. So if you're actually a hyperscaler, you have a lot of interesting data, right, on this, because you have sort of this statistical sample of like how the faults are distributed, how do they look like, when do they occur, what kind of software it impacts, and so on. So that is very valuable information, but it's hard to get that information. So that's why we resorted to sort of building this bottom up. And this workflow totally can be used, of course, by Intel. And it'd be great if we get that kind of information rather than just relying on open designs, right? But this is sort of the methodology that we're laying out, that, you know, this is how we would reason about it. Yeah.
kind of.
Maybe I missed it, Baris, but you had this little snippet of code showing that a program could, run the instruction multiple times, and then so that implies, and maybe this is so, I just don't know. That implies that these things are really, really flaky. Like if it's wrong one time, if I execute it 2 times or 3 times or 4 times, it's unlikely that it will be wrong every time. And is that true?
That is true. Well, we know that may be true. Yes. Yeah, that's right. That's right. Yeah.
I'm convinced. So that doesn't work.
Well, there is stickiness in certain cases, and some of them go away. We know that some of them go away when you run them multiple times. Yeah. So,
but some of them don't.
Well, that's the AES case. So like it depends on how broken the thing is.
Just curious. I was surprised by that. So.
A lot of those BPI effects, you have strong short-term effects.
That's
in
right.
the space of minutes, and then you have years-long effects that are a little bit different. And so if it's one of those short-term effects that high temperature caused it. Yeah.
Thanks.
Yeah, I was curious. Kind of what the current understanding of where software where silent data corruption is coming from. I thought that the model was interesting. That okay, we've got this aging model, for example, and does this statistically, if I run the analysis on a chip and pick the 1% of most vulnerable to aging gates, have I explained 10% of silent data corruptions or 90% of them?
We do know from VLSI research literature that the MBTI effect is the most prominent one. That we know. That's where the most focus has been. It's not the only kind of fault model. Yeah, right. So
I was just gonna say you got PBTI. So I mean, if you're talking about inverters and SRAM cells, this is a different ball game. Yeah. You care about the size of your relative transistor.
But specifically getting at your question, like what percentage we're covering, I don't know that we have that that information. It seems like to get that, it would be good if you could sort of like marry this bottom up knowledge with let's say what the hyperscaler has.
I suppose if a hyperscaler identified a set of machines that they put a finger on saying this one seems to be bad. Now you could ask, well, exactly. Is this consistent with my hypothesis of how it might have failed? Precisely. If it was one of these things. Yeah. Okay. Yeah.
So super fascinating work. I love this. Representing kind of the hyperscaler space here. We've gotten good at identifying flaky memory because we can compare what we know should be in the, we know should be in the page by what we actually read back from the page. Galen had some nice studies on that. We've gotten pretty good at identifying eventually flaky routers and things that corrupt packets in flight because we see the crypto checksums fail as we try and decrypt the stuff on the other side of the network. But for this kind of stuff, I mean, what are the hallmarks we look for? I mean, I got to tell you that like routers, which I'm very familiar, have a habit of saying, "Oh, I have crashed because there's some hardware failure."
Yeah,
and I actually don't believe them because usually what they mean is that there's some device driver issue and send an unmaskable interrupt, which they didn't caught that crashed their service. Are you telling me that, oh no, some of those might actually be aging transistors?
It could be
crashing thing. And how do we, what data would we have that we could go through to try?
So whatever is available. So there's a reason why we picked the floating point unit, right? So the evidence that it's published by a scaler led us towards that direction because we knew that they've observed and they publicly talked about it, that floating point computations can be pretty flaky. So that's sort of one thing that drove us. But besides that, there's little data actually out there that is publicly available. So it is going to be interesting for us to look at different functional module designs and see, whether misbehaving specific modules can actually really impact programs in production in unexpected ways. So it'd be great if there was more guidance, let's say, so that we knew like which functional units to go after.
I will say that one of the things that we've been trying to find in applications is cases where essentially all of your checksums are correct, but the data is wrong. Because the assumption is that early in your computation, something went wrong in your computation. And so by the time you computed checksums down the line, everything looked great. But you can retroactively say that application logic is incorrect. And that's a case where if you don't see a bug in the software, it seems plausible that you could argue there's an SDC.
So thank you. Thank you.